Hello, calculus students, and welcome back. And this is our last lecture. This concludes the BC syllabus. So it's a big day, and this is all about polar functions, which is a kind of cool way to stop. So let's dig in. So you've been living your life so far, your mathematical life, in the world of coordinates like this. And these are known as rectangular coordinates. There's another way to think of the plane, and another way to actually coordinatize it, and that's in terms of r and theta. And essentially what we do here is, for example, if we want to think about the point 230 degrees, then the way that looks is we have an angle in standard position with length 2, and that point then is 2, 30 degrees. And that's essentially the idea of determining a point based upon the angle that it makes with the positive x-axis and how long it is. One of the things that you'll notice is that there's a lot of ways to name a point in polar coordinates. In rectangular coordinates, there's only one way to name a point. But, for example, let's change colors here. We have 230. Well, that's the same as 390 degrees. And that's the same as 2 minus 330 degrees. And finally, it's the same as minus 2 and 210 degrees, etc., etc., etc. So a lot of different ways of naming the same point. Each of these names, however, gives you the only one point. So let's talk about how we can go back and forth between rectangular and polar. For example, suppose we have some point here, and its coordinates are x comma y, and we want to name it in rectangular form. So what that means is we need to know what theta is and what r is. Well, since this point is x comma y, we know that this length is x and this length is y. So therefore, r is just the square root of x squared plus y squared, and theta is the arctan of y over x. So that's how we go from rectangular to polar. Now let's go the other way. So here we have a point given in polar coordinates. So this point is r comma theta, and we want to express it in rectangular form. So just as before, we draw a line down, and what we're looking for is the x and the y coordinate. Now, what we know is that the cosine of theta is x over r. So that means x is equal to r times the cos of theta, and similarly y is equal to r times the sine of theta. So the coordinates of this point then, written in polar form, are r cos theta, r sine theta. And so you see exactly why trigonometry is such a prerequisite for calculus. So when we think about graphing a polar curve, something of the form r is equal to f of theta, we get some really cool pictures, some pictures that aren't as easy to graph in the rectangular world. So I'll give you a couple of examples of these, including the graphs, and hopefully you can appreciate how neat some of them are. And really, until you get an idea of what each graph is like, you need to kind of do these simply by a table of values and getting some sense of how it's behaving. So here's our first one. Suppose we want to look at the graph of r is equal to 2 minus 3 times the sine of theta. Let's see what that looks like. So you see that is a pretty cool graph. One of the things to notice is this little inner loop right here. Kind of neat. So here we see the graph of 3 plus cos of theta. Looks kind of elliptical, doesn't it? Let's look at a few more. Okay, so I've given you two graphs here. And these are both examples of what we call Rose curves. Here is 3 times the cos of 3 theta. So from here to here is 3. And notice there are 1, 2, 3 petals on this rose. Now let's look at the sine of 4 theta. So, you know, the length of any of these is going to be 2. And how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Now, cosine and sine don't determine how many petals there are. That's determined by the coefficient on the theta. If the coefficient is odd, how many petals do you think you'll have? And if the coefficient is even, how many petals do you think you'll have? Why don't you test your hypotheses by pulling out your Inspire and checking it out. So let's talk a little bit about how we can change a polar equation from polar form to either rectangular or parametric form. So first of all, let's talk about how we get to rectangular form. And there's usually a little bit of trick here. Let's change our color. And so what I'm going to do is take this equation that I have and multiply both sides by r. And that'll give me r squared is equal to 3r plus r times the cos of theta. Now, do you remember what r times the cos of theta is? And do you remember what r squared is? So this simply becomes x squared plus y squared is equal to 3 times the square root of x squared plus y squared plus x. And you can fiddle with that a little bit, but there it is. Now it's changed from being in polar form to rectangular form. So now let's look at how we would go and write our polar equation in parametric form. Okay, and so let's remember these conversions. X is equal to r cos theta. Y is equal to r sine of theta. There we go. So what that means is, given that r is equal to 3 plus cos theta, then we can write this in parametric form as x is equal to r, that's r, times cos theta, and y is equal to r times sine of theta. And so now we've taken the equation written in polar form and expressed it as a pair of parametric equations. So now let's do a little bit of calculus and talk about the slope of a polar curve. You should believe from the couple of polar curves that you have already seen that they're smooth, and so therefore they will have a derivative. And when we graph them, you can think of them as being in the xy plane as well as the r theta plane. So this is something which we've already looked at in the parametric world. If we want dy dx, then all we want to do is do dy d theta over dx d theta. Now let's remember, y is equal to r times the sine of theta, and x is equal to r times the cos of theta. You see where this is going? So let's look at an example. And let's look at, say, r is equal to 2 times sine of 3 theta. It's a Rose curve, right? Okay, so here we go. This is going to be a long one. dy dx is equal to dy d theta over dx d theta. Now, dy d theta is the derivative of r times the sine of theta. So that's going to equal the derivative with respect to theta of r, there's r, times the sine of theta, all over the derivative with respect to theta of x. And x is r times the cos of theta. Get it? So I'll write out the answer, and you can check me to see if I made any careless mistakes, but it's basically just using the product rule. So go ahead and check my calculations and see if I was able to get it, but there you go. That is dy dx. How ugly is that? How messy is that? That's life. Okay, so now let's talk about the area enclosed by a polar curve. Now, you know, when we were finding the area under a curve in the Cartesian world, we used rectangles. What I want you to think about here is, imagine that we have some polar curve, and rather than rectangles, what we're going to do is look at little wedges, or like pieces of pizza. And for, it's hard to read, I'm sorry, this is delta theta. But for delta theta sufficiently small, both of these r's are essentially the same. And that's the same as when you're doing a Riemann sum and you're looking at rectangles and you make delta x sufficiently small. It really doesn't matter where you pick your height. Same thing here. So this little sector that I want to find the area of is like a sector of a circle. And to find the area of a sector of a circle, we simply use proportions. So the area of a sector over the total area of a circle with radius r is equal to the central angle divided by the complete set of angles in a circle. And so what that tells us is that the area of a sector of a circle is going to turn out to be 1/2 r squared delta theta. And so the area enclosed by all of these things is just what you get when you add up 1/2 r squared delta theta. And if I let delta theta become small enough, and in fact delta theta approach 0, then what we have is obviously a definite integral as we go from one value of theta to the next, r squared d theta. And that there is the formula for the area enclosed by a polar curve. It's a pretty cool formula, and it all comes from this little work right here. Okay, so let's put it to work. Okay, so here's an example. Let's find the area enclosed by the graph of r is equal to 2 times 1 plus cos theta. And here's the graph right here. Now, it's going to take 2 pi units to get all the way around. And it's important to understand how much you have to use, what range theta has to go through so that you get the full graph but nothing more. And so, therefore, the area of this is going to equal 1/2 times the integral from 0 to 2 pi of r, which is this, squared. And if you perform the operations and do some integration tricks, this is going to come out to be 2 pi. And certainly you could use a CAS tool here to get that integral. Let's look at another example, perhaps. Yeah. Okay, so check this out. We want to find the area of the inner loop right in here for this polar curve r is equal to 2 cos theta plus 1. So really what that means is we have to know where does that inner loop begin and when does it end. And a loop begins right when r is 0. So what we're basically going to do is say when does 2 times the cos of theta plus 1 is equal to 0. And it shouldn't be too hard for you to figure out that that means theta is 2 pi over 3 and 4 pi over 3. So that loop starts to get drawn as we move along here. It starts to get drawn at 2 pi over 3 and it finishes being drawn at 4 pi over 3. So therefore this area of the inner loop is going to equal 1/2 times the integral from 2 pi over 3 to 4 pi over 3 of r 2 times the cos of theta plus 1 squared d theta. And if we use some CAS tool here, we'll learn that this area is 0.544. Kind of neat. All right, let's stop there for a sec and move along to something different. So here we want to find the area between two curves. And as long as we know that R2 is greater than or equal to R1, you shouldn't have a lot of trouble believing that the area is simply going to be the difference of these two areas. So going from, let's say, theta 1 to theta 2 of r sub 2 squared d theta minus the integral from theta 1 to theta 2 of r sub 1 squared d theta. So that's very similar to some of the work that we did with rectangular curves. So if we look at an example, this maybe will help you understand it a little bit more if you need that. So on this example, we want to find the area inside the circle, r equals 1, and outside the cardioid, r equals 1 minus cos theta. In other words, that's this region right in here. Now, what you can tell is this is going to go from minus pi over 2 to pi over 2. So I want to find the area from here inside the circle and then subtract from it that much. And so hopefully you can see that this area is going to equal 1/2 times the integral from minus pi over 2 to pi over 2 of the outermost one squared minus the innermost one squared d theta. And you can use a CAS to compute that. But that's how we find the area bounded by two curves essentially. So here is our last topic in the last section, in the last chapter. And what we're looking for here is the formula for how to compute the length of a polar curve. So one of the things that we should remember from the parametric world is that the length is equal to the integral of dx d theta squared plus dy d theta squared d theta. Furthermore, let's remember that, if we have some function r is equal to f of theta, and x is equal to f of theta times the cos of theta, and y is equal to f of theta times the sine of theta. So take a second, maybe to pause, and see if you can tell how this is going to go. So I'm going to take some time and I'm going to write out what dx d theta is, what dy d theta is, then what dx d theta quantity squared is, what dy d theta quantity squared is, and finally what the sum is of dx d theta squared and dy d theta squared. And it's going to be pretty cool. So I'll do all this writing and you can just look at it at your leisure. So, as I said, just take some time and go through this using the product rule. This is pretty messy, and this is pretty messy, and I've run out of room on this particular slide. But think about what happens when I'm going to add these two together. Bang, bang, bang. So let's finish this up on the next page. So when we add them up, the middle terms cancel, and because sine squared plus cos squared is 1, we get this ridiculously simplified version for what dx d theta squared plus dy d theta squared is equal to. And that really is just r squared plus dr d theta. So therefore, arc length is just going to be the integral from theta 1 to theta 2, depending upon what they are, of the square root of r squared plus dr d theta squared d theta. And that, oh students, is the formula for the arc length of a polar curve. And so finally, let's look at the length, let's say, of r equals 3 plus cos theta. So we want to find the length of this curve, in other words, the circumference of this curve. We go from 0 to 2 pi, and r is equal to 3 plus cos theta, and we note that dr d theta is equal to minus sine of theta. So therefore the length is going to be the integral from 0 to 2 pi of the square root of r squared, which is 3 plus cos of theta squared plus dr d theta squared d theta. And again, of course, with a cast machine, we will learn that this total circumference is 19.38 about. And there you go. And so that basically takes care of BC calculus. Thanks for hanging in, and I'll smile at you as you go about your way. So congratulations, all of you BC calculus students. We are done. It's been fun doing this with you. I hope you enjoyed it. And I am Dick Peller. And I am out of here. Ciao, ciao, ciao.